So friends, we deal today in the thermal properties of matter and thermal expansion. We know that most substances, they expand on heating and they contract on cooling. It's a common observation, which means that change in temperature causes change in the dimensions, and this is called thermal expansion. It could be called also thermal contraction. We can categorize that in three parts: linear expansion in the case of a rod, area expansion in the case of a plate, rod is here, and volume expansion in the case of a voluminous body. Now, if delta T is the change which appears to be here, then the change delta L in the length in the case of linear expansion divided by L, that is the fractional change, is proportional to delta T, which means delta L upon L is equal to a constant times delta T, and this constant alpha L is called the coefficient of linear expansion. The coefficient of linear expansion, and it is a function of the material of the rod. Normally here we are talking about the temperature changes lying between 0 degree and 100 degrees Celsius. Similarly, for this case of a plate being subjected to a change in its temperature by an amount delta T, the fractional delta A upon A, which is of course a number, is proportional to delta T, or I can write that delta A upon A is equal to constant times delta T, and this constant becomes twice the value of alpha L. Similarly, in the case of volume expansion, where I have just taken a cubical body, expanded it in the red margins, that is, expansion has taken place, and when the temperature is raised by delta T, we find that delta V upon V is proportional to delta T for that range of temperature. So it gives delta V upon V as equal to 3 alpha L into delta T, where 3 alpha L is the constant of proportionality of the system. Okay. We can look here. Here I have just given the value of alpha L for various materials, starting from aluminium, brass, iron, copper, silver, gold, pyrex, glass. Okay. You can see that the expansion is large for metals and alloys, and in all these cases, but for the pyrex glass it is manifold less for the expansion. Also in the case of what we take as lead, the expansion, the alpha value is even less than 0.32. Okay. Now, as I told you that the length L goes to become L plus delta L, there is an expansion of delta L, but for the case of volume, we define the same way, that alpha V is equal to delta V upon V, whole thing divided by delta T. Okay. Why I have taken this is to tell you that it's not as linear as in the case of these values of temperatures 0 to 100 degrees Celsius. As the temperature is raised, so this coefficient becomes a function of temperature too. Function of temperature too. And we'll just interestingly see this situation with the help of a graph which shows the value of alpha V changing with temperature. So this volume expansion, alpha volume, this was 3 times alpha L, the linear expansion for the solids, for the systems that we have been talking about, normally at lower temperatures. But as I said, that this alpha V, which is again defined in the same way, delta V upon V divided by capital T, okay, and this one is not a constant for all values of temperature. As the temperature rises, and which we can see here for brass, for example, that for metals, I have shown that for low temperatures, this is a straight line, okay. Thereafter, its slope changes, and the slope keeps on changing. That means once there is a non-linearity which comes in the figure, in a diagram, in a plot like that, that means now y has become a function of x. So similarly here, alpha v becomes a function of t, and non-linearity creeps into the system. You can see that there is a behavior after 200 Celsius, after this is temperature in degrees Celsius, okay. We take the temperature in degrees Celsius, which is more practical as compared to the Kelvin temperature. All we have to do is we have to add 273.15 and I'll get that. So this is a rough graph from where we understand that the first of all there is a rapid change, and after 500 Celsius or more, then more or less there is hardly any change in the value of the volume, and this is how things work. I have enumerated the value of alpha V for several substances. Aluminium 7 into 10 to the power of minus 5, it's all in the units of 10 to the power of minus 5. Brass is 6, iron is 3.55, ordinary glass is 2.5, Pyrex glass is 1.0, paraffin, which is an organic substance, 58.8, hard rubber 24.0, alcohol maximum 110.0, water 20.7, mercury 18.2, and the minimum value that we obtain in volume expansion is almost there is no expansion for rise in temperature, per degree rise in temperature, okay, and that is in the case of what we call invar, which is a special alloy of iron and nickel, but the value is 0.2. So we can see that various substances in which 3 of them are found in the liquid form, okay, the name suggests like that, and paraffin also kind of semi-liquid, it has got a very low melting point, etc. And ordinary glass and Pyrex and this and that, we find that the value of the alpha V has typical values given like this. So if we have to use several materials with each other, over each other, then we have to make calculations for the various values as to how we are going to obtain. If we have laminar kind of adjustment, then accordingly we have to do. The most interesting example is water. Water has an anomalous behavior in that if we, I'll not take it like this, okay, from 0 Celsius when it is in the form of ice, from there if you heat the water, then what happens is that the volume of the water decreases until 4 degrees Celsius, and thereafter it starts increasing with the rising temperature. On the reverse journey, as you go there, so it expands and up to, contracts up to 4 degrees Celsius, and thereafter it expands. Now this behavior, which I have also shown in the density of the water, 5 degrees Celsius and 10 degrees Celsius. 10 degrees Celsius, the value is 0.99970, and at 5 degrees Celsius, okay, it's almost 1.00000. It's actually, this peak takes place at 4 degrees Celsius. Now this anomalous behavior of water is very useful to us, very useful to the environment, in that in water bodies, when the temperature falls and falls and falls, so first of all what happens is that the layer, upper layer, okay, that is made into a solid form, and the heavy water, it goes inside, and along with the heavy water go the marine objects which live inside, like fishes and other beings, okay. And as the temperature is decreased, so what happens, that this frozen layer becomes thicker and thicker, but the bottom of the lake, or the bottom of the water body, is still at a temperature so that it is in the liquid form. The fishes and the other marine objects, they can swim inside, move inside from one place to another place, and of course they can breathe the oxygen which is dissolved inside the. So this is the anomalous behavior of water, which is an interesting behavior. We must be careful, because we can be taken for a ride. If somebody asks what happens at about 4 degrees Celsius, you must be very clear that the density is maximum at 4 degrees Celsius. This side and that side, it falls rapidly. So we found that the volume expansion in the case of a liquid at high temperatures, there is a plateau, and this plateau means that it is independent of the temperature at those temperatures. So alpha V, experimentally determined value, is because of the plateau. That value does not depend upon the temperature. Gases has a totally different behavior. At ordinary temperatures, they expand more than the expansion in the gases is more than the expansion in solids and liquids. And also alpha V is quite dependent on temperature. So we can go back to the case of low density gases, which we call the ideal gases, okay? The special gases known as ideal gases, where the gas equation PV is equal to nRT. P is the pressure, V is the volume, N is the number of moles, R is the gas constant, and T is the absolute temperature. From this equation that we have, PV is equal to nRT, at constant pressure I can write by differentiation that P delta V is equal to nR delta T. So that now if I divide this equation by this equation, I'll get delta V upon V, and this equation by this equation, RT, R and N will cancel, and delta T by T. So we find that delta V upon V divided by delta T, delta V upon V, whole thing let me make clear, divided by delta T, this is equal to what? This is defined as alpha V, okay, the coefficient of volume expansion for this substance at the given temperature. So this turns out to be equal to alpha V is equal to 1 upon capital T. So more the value of capital T, less the value of alpha V, okay. So there is a temperature dependence, and we can get again, because this is what we get, alpha V into T is equal to 1, and so it is, I'll get again the Y is proportional to 1 upon X kind of a graph, where every point taken over here and we want to evaluate the area will be the same for every other point. Okay. So under those conditions, alpha V is inversely proportional, R is equal to 1 upon capital T, okay, like that. At 0 degrees Celsius, look here, the coefficient of volume expansion is equal to 3.7 into 10 to the power of minus 3 per Kelvin, okay, which I can write as 370 to 10 to the power minus 5 per Kelvin. If just to compare all those values that were enumerated in the table, we find that this value is much larger, okay. So alpha V decreases with increasing value of capital T, which is the absolute temperature. At room temperature, the interesting feature is that alpha V turns out to be at room temperatures 3,300 into, now I have changed it to 10 to the power of minus 6 per Kelvin, which is a very large amount. Okay. Now let us see and take up solid, a cube of side L, and we find that by definition delta L on L is equal to alpha L into delta T. Okay. This is what we get for the linear expansion of the solid rod, which gives delta L, the value is equal to L alpha L into delta T. Okay. Now, for example, if we increase the temperature by an amount delta T, then what happens is the volume increases. And because all sides are equal in the cube, then the volume of the cube is L cube. Volume of the expanded cube will become equal to L plus delta L whole cube. So when I expand this quantity, I get L cube plus 3L square delta L plus 3L, into plus here, plus delta L cube. Okay, so this L cube will cancel with L cube, okay, and this delta L cube and this term containing delta L square, because these terms are negligibly small, and therefore what is left is approximately 3L square delta L, which L square I multiplied by L and divide this thing by L, so I get L cube here, which is the volume, 3V into delta L upon L. Okay, so delta V becomes equal to 3V, delta V becomes equal to 3V delta L upon L. Okay, and I can write this as again 3V alpha L into delta T. So therefore delta V divided by V into delta T here, this we define as delta V, alpha V, which turns out to be equal to 3 alpha L. So alpha V in this case, alpha V is equal to, like I had shown earlier, 3 alpha L. In a similar manner, we can take, for example, a plate of dimensions L by L, in which case we'll have this definition as it is, then the area, delta area or delta S, the surface area, will be equal to L plus delta L whole square minus L square, and then when we expand, then we get 2 L into delta L, okay, and we work out, and in that case we get the area expansion or the superficial expansion. This is equal to 2 times alpha L. The mathematical strategy is the same, but you can work it out as an exercise, additional exercise, and you obtain the two results, that alpha A is equal to 2 alpha L and alpha V is equal to 3 alpha L. Okay, so you can also write that alpha V is equal to 3 alpha L. I can write alpha A by 2. So these are some of the tidbits here and there which you can just derive in a, I won't say in fraction of a second, in a couple of seconds or maybe 3 seconds, and you can obtain the result, provided you know what is the value of alpha L, and from there you get the value of alpha A and alpha V. You can derive very, very quickly. Let us investigate as to what is thermal stress. And suppose the thermal expansion is prevented. The thermal expansion of a rod is prevented by fixing the ends rigidly. Okay, you don't allow the rod to so a thermal expansion will come. Here I am taking a steel rail of length 5 meters, okay, and area of cross section, the two ends, uniform area of cross section, that is 40 into 10 to the power 4 meter square, is 40 centimeters square. We make a change of about 10 degrees Celsius or 10 Kelvin in the existing temperature of this rod, existing temperature of this rail, the 5 meter long rail. We give you the data about the Young's modulus of steel, which is nothing but stress upon strain. Okay, so now of course if it was allowed to have the expansion, then there will be a compressive strain. Delta L upon L is equal to alpha L of steel, which is also given to us. Alpha L of steel is taken as 1.2 into 10 to the power of minus 5 per Kelvin. Delta L upon L is equal to delta L steel into delta T. So we calculate, putting these values, delta L upon L is equal to the alpha L of steel 1.2 into 10 to the power of minus 5 into, of course, what's that, 10 degrees Celsius or 10 Kelvin rise in temperature, and this turns out to be equal to 1.2 into 10 to the power of minus 4. What should be the unit here? No unit, because the units of delta L are one and the same. Now, we define the thermal stress which will develop there will be the force on these sides divided by the area of cross section, and this stress upon strain is equal to Y. So Y is equal to stress upon strain, so stress is equal to Y into strain. So I am writing this Y steel into delta L upon L. Substitute the values, 2 into 10 to the power of 11 Newton per meter square into 1.2 into 10 to the power of minus 4, what we have received here, obtained here as delta L upon L. So I obtain a result which is 2.4 into 10 to the power of 7 proper units, which is Newton per meter square. So if I have to find out as to what is the delta F which will develop over there, I just multiply this by A and I get here 2.4 into 10 to the power 7 into 40 into 10 to the power of minus 4, which turns out to be this into this, turns out to be approximately 100, and so it is because this will be equal to 4 into 24 is 96, which is 9.6 into 10, and this turns out to be equal to, in the nearness of, in the vicinity of 10 to the power of 5 newtons, which is a very large amount of force difference. So there is possibility that this steel rail may bend a little bit, okay. So when it bends, one side becomes concave, the other side becomes convex. We talk more about other properties like the thermal capacity, etc. in the next lecture. So long, see you, please, okay, bye.